Hi guys, how's it going? I'm having a good time telling you about some of the more speculative ideas of modern physics. Taking a walk on the wild side, so to speak. In earlier episodes, I talked at length of the rules that govern the universe. But what if the universe isn't the whole story? What if there are many universes? What does that even mean? That sounds like an excellent topic to explore in this week's episode of Subatomic Stories. The word universe literally means everything, the whole shebang. All of the stars, galaxies, dark matter, dark energy, as far as the most powerful telescopes can see. It's even farther than that. It's everything. But everything doesn't always mean everything, I guess. Scientists are kicking around an idea that there isn't just one universe, rather there are multiple universes. The word we use for this is the multiverse. So why, just why, do scientists think that the multiverse idea is even the tiniest bit reasonable? And what, exactly, is a multiverse? Okay, this multiverse idea seems really dodgy. Why is it considered a credible possibility? Well, it comes down to one question. Why is the universe the way it is, and why is it so suitable for human life? Do the laws of physics make it inevitable, or is it all a vast and cosmic accident? There are many parameters that govern the universe, from the respective strengths of electromagnetism and gravity, to the ratio of the mass of neutrons and protons, to the mass density of the universe, to the amount of dark energy. They all have a specific value. But it's interesting to ask just what would happen if they were changed just a little. If our universe is inevitable, then changing these parameters by small amounts wouldn't change the universe much. It would look more or less like it does now. But that's not the situation. In case after case, a small change in a parameter would make for an entirely different universe. For instance, if the energy density of the universe were just a tiny bit different, one of two things would have happened. If we're just a tiny bit higher, gravity would have been so strong that the expansion of the universe would have reversed itself very quickly, and the entire cosmos would have collapsed into a black hole long before life could have formed. Or, if the density were a little bit lower, the expansion of the universe would have been so high that matter would have spread out so smoothly and so quickly that galaxies, stars, planets would never have formed, and certainly humans could never exist. There are dozens of examples of instances where small changes in parameters would result in a universe that is completely inhospitable to life as we know it. The terminology that scientists, philosophers, and theologians use for this state of affairs is that the universe is finely tuned. Something was responsible for the values of parameters that resulted in our comfy universe. One possible explanation for this fine-tuning is called intelligent design, which says that the universe couldn't exist without a mindful creator who set the parameters the way they are. Such a position is consistent with existing data, but it's inherently not scientific. It's not testable. So what can science do for us? That's where the multiverse comes in. The multiverse hypothesis avoids the entire problem by saying that there's no fine-tuning. Rather, there are many, many universes, each with very different laws of physics, and, so the theory goes, we inhabit one of them that just happens to have the laws and parameters that are congenial to human life. Those other universes might well be lifeless. This is called the anthropic principle. Essentially, the multiverse idea is a scientific counterpart to intelligent design. They both attempt to address the same intellectual conundrum. So, scientifically speaking, what might a multiverse be? Well, as you'd expect with such speculative idea, there are a couple of options. The first one isn't all that contentious. I've spoken in previous episodes about how scientists know that the volume of the entire universe is at least 125 million times bigger than the visible universe. And if the entire universe is infinite, then there are an infinite number of pockets of the universe similar to ours. If the laws of the universe change slowly enough that they seem constant in our visible universe, but fast enough that they're different in distant corners of the universe, then each of these pockets of the overall universe might be quite different from what we see in the nearby universe. And of course, we live in a pocket of the cosmos that's congenial to us. Another idea of the multiverse is more speculative and is built on the idea of inflation I mentioned in episode 27. As each universe buds off from the others, the physical laws in the new universe might be different from ours. And if the idea of eternal inflation is true, then there are an infinite number of universes out there with different rules. So that's the big idea. The multiverse was invented in part to explain why the rules of our universe seem to be so finely tuned. And there are a number of credible ideas as to how different forms of multiverses might exist. If you want to learn more about this in a little more depth, I made not one, but 2 long-form videos on the subject matter. The links are in the video description below. The idea of the multiverse is testable, at least in principle, although solid predictions are few and far between. Some multiverse ideas predict such things as the cosmic microwave background radiation that is the remnant of the Big Bang might have subtle features that reflect other universes. But while some researchers claim to have seen such signatures, the scientific community has not yet embraced these results as definitive. So now you're probably asking yourself, should I believe in multiverses? Or maybe you're asking, does Dr. Don believe in them? I can't answer the first question, but I can the second. No, I don't believe in multiverses. I think they're awfully speculative. On the other hand, neither do I disbelieve in them. I regard them as an intriguing hypothesis, and the fine-tuning problem does need an answer. But in order to elevate the multiverse idea to the level of real science, we need more testable predictions, and those are hard to come by. I think that for the moment and for the foreseeable future, whether the multiverse is real or not is an open question, and any reasonable person would have to view the hypothesis with a healthy dose of skepticism. And, speaking of questions, what questions do you guys have for me today? Question time is always fun, so let's get to it. Jose Alejandro asks why dark energy is called dark energy and not something like anti-gravity. Hi, Jose. How are you? Buff icon. You've been working out. So this question I can answer. The name came from this one guy by the name of Michael Turner. He is a leading cosmologist who is a professor at the University of Chicago for decades. He also does some science outreach, and he and I have been on radio shows and on stages together. The story is, as Michael tells it, is that he was at a conference where people were discussing the first evidence for the accelerating expansion of the universe. He and other cosmologists knew how to modify Einstein's equations to cause the expansion of the universe to speed up. They didn't invent the idea, Einstein did, but that's another story. In any event, during his talk, he tossed out the name dark energy as it was another cosmic mystery like dark matter, and the name stuck. I don't like the name anti-gravity because it would imply that it was something new, different from Einstein's gravity. But in fact, the accelerating expansion is easily explained by Einstein's theory of gravity. You just have to imagine a different kind of energy from familiar energy. That's why the term dark energy is better. Scientia and Veritas criticizes the idea of supersymmetry by noting that no selectrons have been observed. Hi, Scientia. It's true that all supersymmetric theories predict cousin particles for the known familiar ones. For every fermion electron, Susie predicts a boson selectron. For every boson photon, Susie predicts a fermion photino. And this is true for every known particle of the Standard Model. If the symmetry of supersymmetry were, in fact, symmetrical, the selectron would have the same mass as the electron. But if it did, we'd have discovered it by now. In fact, we would have discovered supersymmetry before it was proposed in the 1970s. Indeed, when it was proposed, it was already known that true mathematical supersymmetry wasn't real. It was ruled out the day it was proposed. But scientists also knew that many symmetries are broken. Electroweak symmetry, in which photons and Z-bosons are both massless, is broken by the Higgs field. So supersymmetry, if it exists, is an example of a broken symmetry. If it exists, something makes the cousin supersymmetric particles more massive than the familiar ones of the Standard Model. So, if you buy into the idea of Susie, then you're buying into the idea of broken Susie. And if the masses of the supersymmetric cousin particles are too high, then the idea becomes more pedantic and less useful to solve current theoretical problems. And with the data from the LHC, we can say that the mass of Susie particles are pretty high, and that means the interest in the idea is beginning to wane. But people still search for the supersymmetric cousins. They still could exist. Zirkman notes that since the Higgs field turns off at high energies, does that mean that particles moving very fast have no mass? Hi, Zirkman. Good question. It's easy to get confused. When scientists say that the Higgs field becomes zero at high energy, they mean when the energy is concentrated in a single location, when space is heated up, so to speak. They don't mean when a particle is moving at very high speeds. After all, relativity says that you can do your calculations in the frame of the moving particle. In that frame, the particle is stationary and therefore has minimal energy. No, scientists instead talk about the energy at the center of a powerful collision, or when the energy density is very high, like after the Big Bang. Then the energy was high everywhere, and under those conditions, the Higgs field was zero. Does this help? Justin Mueller asks, what leads to the prediction of the mass of the Higgs boson being more massive than observed? Hi, Justin. The answer to your question is very complicated, and I made an entire video about it, which is worth your time. The link is in the description. But let me sketch it out briefly here. When scientists try to predict the mass of the Higgs boson, they have to include a bunch of quantum effects over a range of size scales from big to small. Size is inversely related to energy, with small sizes being large energy. So when they do the calculation, they add up the quantum effects for energies ranging from 0 to the highest possible energy. The math is hard, but the final result is that the quantum corrections to the mass of the Higgs boson is equal to the highest possible energy squared times some constants. The highest possible energy is ginormous. Square it, and it's super ginormous. That means that in order for the prediction of the mass of the Higgs boson to be reasonable, those constants need to be nearly zero. Something has to tame that ginormous number, and that's why supersymmetry is theoretically interesting. If supersymmetry is true, then that constant is exactly zero. Watch that video if you want to learn more. Criminy notes that I said that dark matter could be like epicycles and asks if the Standard Model could too. Hi, Criminy. Actually, I don't think so. The Standard Model is incomplete, but I think it's unlikely to be truly wrong. The Standard Model is more like Newton's theory of gravity, which works fine, but was replaced by the more general theory of general relativity. Newtonian gravity is still right, but it doesn't work in all situations. I expect that when the Standard Model is replaced, the new theory will have all of the features of the Standard Model embedded within it. The Standard Model won't get thrown away, or at least that's what I would bet. DPollock59 asks why, when two neutron stars merged 130 million years ago, the gravitational waves got here first. Hi, DPollock. That's actually easy. Gravitational waves are emitted as the neutron stars orbit one another before the collision, while electromagnetic radiation is emitted in the actual collision. Gravitational waves got here first because they were emitted first. Good question. Scott Hammond asks if there's any evidence that the strong force and electroweak force unify in a grand unified theory. Hi, Scott. Yeah, the answer here is a bit murky. Mostly, I would say no. A lot of this unification idea is a theoretical prejudice, albeit one with a lot of historical precedent. But there is one niggling hint that isn't exactly persuasive, but it does give a sense that the idea might be true. It turns out that while we can say that the strong force is stronger than electromagnetism, which is stronger than the weak force, it's also true that the strength of the forces changes with energy. Remember that high energy means small sizes, and here is a plot of data that shows that as the energy increases, forces change in strength. Now this plot is confusing because the bottom is strong and the top is weak. It's weird, but that's just how it is. Take a second to get used to it. According to our current measurements, we see that the strong force gets weaker, as does the weak force, while electromagnetism gets stronger. You'll also notice that the weak force is stronger than electromagnetism because this is a plot of the intrinsic force, while the force we actually see also includes the mass of the force-carrying particles. But that's a video of its own. Now, let's project the trends to even higher energies. You see that the forces all become the same strength at high energy, just below the Planck energy, in fact. They don't become the same strength at the same energy, but the trend is suggestive. And here's a fun fact. If you add supersymmetry to the Standard Model, you can get all of the forces to merge at a single energy. This is another reason that people liked the idea of supersymmetry in the past. This trend of changing of the strength of the forces as a function of energy is one of the stronger bits of evidence that the forces merge at higher energy, but it's not conclusive. Like I said, it's mostly a theoretical prejudice. That last question was pretty technical, so maybe it's a good time to stop and think it through. If you're enjoying the series, be sure to subscribe to the channel and share the video with your friends. Hopefully, your friends are like us, the kind of people who know the deepest truth that, even at home, physics is everything.